All right, so now what I can do is, okay, what is the velocity when my time is 0.5, which is the question that's being asked, right? What will be that velocity? Well, the velocity will be 15 minus 15 to the e 0.5 divided by 5. So to the e to the minus 0.1. And this happens to be, what did I get here? This happens to be 1.427. 1.427. And this is going to be meters per second. How do I know it's meters per second? That's actually a question that's worth asking. Remember that we knew the acceleration was meters per second squared. Where are we? Here. We knew the acceleration was meters per second squared. Okay? And then we're integrating with time and time in seconds. So we'll multiply meters per second squared times the seconds. That's how we know it's meters per second. Okay? That's how we can confidently say it's meters per second. The other thing we can do, and this is also interesting, is when we put in these boundary conditions, right, this is t equals 0 seconds. And also, this is v equals 0 meters per second. So therefore, when we substitute here, this is meters per second. We remove any dimensions out of here. We know this is coming as meters per second, so therefore this also has to be meters per second here. Okay, so this number keeps going. This is just an approximation of it. All right, let's move on. So we found out the position. Next thing to find out is what is the velocity. Next thing to find out is what is the position. So we knew this much. We knew this much, and now we want to know what is the position. So it's the same basic principle. We're just going to do it one more time. The basic principle is, we know that the rate at which the position changes with time is the velocity. And we happen to know the velocity is 15 minus 15 e to the minus t over 5. So therefore, if I take that dt, send it to the side, multiplying these guys, I can go ahead and integrate on both ends. And once again, I can keep this as an undefined integral, or I can go, okay, from 0 to x, from 0 to t. And again, slightly different ways of doing it, but you're going to get exactly the same answer at the end. Okay, so what do we do next? We go ahead and integrate. Here we're going to get x plus that constant. On both sides, we're going to get a constant, so we can go ahead and make sure we have a constant here, plus these two integrals here. And the integral here is 15 dt, so that's going to be 15t plus a constant. The constant is just going to be sum of all the constants, so we have a final constant at the end. And over here we have minus 15 integral of e to the minus t 5 dt. And this is super familiar, right? It's exactly the same as before. We can do exactly the same thing. Do it by substitution, substitute again. We're going to get them negative 5 coming out of it once again. So we need to multiply this by the negative 5. Okay, so this is going to be exactly the same thing. We're going to get a constant here plus 15t minus 15, and multiply it's minus 5 e to the minus t over 5. Once again, boundary conditions. So when my time is 0 seconds, my position is 0 meters. So if that's the case, then 0 has to be equal to that constant plus 15 times 0, so this goes away, minus 15 times minus 5 e to the 0. So this is 1, this is minus 5, this is minus 5 times minus 75, that's 75. So the constant will be, let me just do one more step. So constant equals plus 75, and therefore the constant equals minus 75. Okay, and if this is true, then what we do here is substitute where we have a constant, we just put the minus 75. So this means that my position, or the way that my position varies with time, equals minus 75 plus 15t minus 5 times 75, that's 75 to e to the minus t5. This is how the position varies with time. And we have a bunch of big numbers there, so we can get the 15 and take it out of the, just put it in evidence if we want. But the important thing here is, what is the position at 0.5? Position at 0.5 will be minus 75 plus 15 times 0.5, so 7.5 there, minus 75 times e to the minus 0.5 divided by 5. And what did I get out of this? I got 75. I feel like I have something backwards here. Negative 75. Oh no, never mind. Positive 75. Negative. Yep. Oops. There you go. So I got out of here. This is 3.3620806, and it keeps going. So let's go ahead and approximate this to 363. And this is in meters because everything else was in meters, and because the problem statement said so in the beginning. Okay, so this is the answer for the position. With this equation now at hand, and let me go ahead and make this a bit less daunting. Let me go. Same thing as 15 that multiplies 5 to the e minus t divided by 5 plus t minus 5. I think that's a bit less daunting. Same thing, right? So now that we have this equation, we can find out what's the position of this given particle at any time that we possibly want to find. We can find it at time equals 0. We can find a time equals 1, 2, 3, whatever you want. Okay. At 0.5, it happens to be at 3.6 meters of distance. And same thing goes for the velocity, right? Where's our final number for the velocity? Here we go. At 0.5, the velocity happens to be 1.427 approximately. But with this equation here, we can find velocity at any given time we can possibly want. All right. So again, the whole basic principle around this is that the velocity is nothing but the way that the position varies with time, and therefore we can use it to find out the position equation, and likewise acceleration is nothing but the way the velocity changes with time, and therefore we can use it to find the velocity equation. All right, so I hope this was useful. If you have any questions, as per usual, just leave them down below in the comment section. If this video has helped you out, consider giving it a like, and we'll talk soon.